We're in Chapter 2, Linear Equations, and we're working on Section 2.6, Ratio and Proportions. Today our vocabulary is as follows: ratio, proportion, means, extremes, rate, unit rate, scale, and at the bottom here we have scale model. Let's take the first two words. Ratio is a comparison of two numbers by division, and a proportion is an equation that consists of two equal ratios. So for instance, if I were to say 2 is to 5 as 4 is to 10, this would be a proportion because they are equal ratios set equal to one another. This is a proportion. The next two words, means and extremes, are used to talk about parts of a proportion. Now remember from the last example we said 2 is to 5 as 4 is to 10 represents a proportion. As you know, ratios can be written in different ways. One way is to write 2 is to 5 as 4 is to 10 using the colons here. So the key to recognizing what the means and extremes are is really just looking at the location of these numbers. If I highlight or underline the word means in blue, I can show you that 5 and 4 are the means. A quick or easy way to remember this is that the means are in the middle. And of course the extremes, as you would guess, are on the extreme sides. So 2 and 10 refer to the extremes. It's a little bit hard to see where the extremes and means are when you're looking at the proportion as two fractions set equal to one another. But if you can identify them, I'm sure you'd realize that 2 and 10 out here, we have the extremes, and then the means are on the inside right here. Our next two vocabularies are rate and unit rate. When we talk about rate, it's a ratio of two measures having different units, and you're probably used to the concept of rate when you talk about rate in terms of speed, like how fast somebody's going. And if you think about that, usually people give rate in terms of miles per hour. Notice that's two different units used to create a ratio. So measures having two different units used to create a ratio. And then the next one we have is the unit rate, a rate that tells how many of one item is being compared to one of another. Okay, so an example is I was at Walmart and I saw 9 oranges for $3, pretty good price. And the fact that we're talking about two different things is considered a rate. So 9 oranges at $3 for, whatever group of oranges I'm talking about, for $3 per group of 9 oranges. And then the unit rate would be now to change this so that we're calculating, and what makes sense is how many oranges I'm getting per dollar. Or I could also calculate how much it costs per orange. Either one is a unit rate, but I'm going to do the one I mentioned first. So I can now figure out how much this costs per dollar by reducing this. I'm going to divide the denominator by 3, so I know I'm dealing with $1, and the numerator is going to be 3 oranges. So now this has become a unit rate. Our next two words are scale and scale model. Scale is the portion of a ratio that indicates the reduced or enlarged size of something, and the scale model is a 3D reproduction of an item that has been increased or decreased in size proportionally. Okay, so our first example, sorry for the overlap in writing here, but I'll explain what it says. It says example 1, determining whether ratios are equivalent. And then the question says determine whether 2/3, this fraction here, or this ratio right there, and 16/24 are equivalent ratios. The way I would probably tell you to do this is to recognize that the relationship between ratios is that they should be equivalent, meaning once you reduce the top and reduce the bottom, you should be able to make two equivalent fractions. So what we'll do is we'll see if there's a number that can, 2/3 is itself, it's reduced as much as possible. Let's see if we can actually reduce 16/24, hopefully you recognize that I could divide the numerator and denominator by 8. Actually, I was going to divide it by 4, but as I looked at it, I realized I could divide it by 8. 16 divided by 8 is 2. 24 divided by 8 is 3. And voila, we have equivalent fractions, which tells me that these ratios, the original ratios, were equivalent. How do you justify your answer? By showing your work. Some of you may have thought, you know what, I can cross multiply, and that's exactly right. If we multiplied across, 3 times 16 is 48, and then 24 times 2 is 48, you get two equivalent numbers. You know, sometimes it's said the product of the means is equal to the product of the extremes. We'll talk a little bit more about that. But in the end, there's a few ways to get around it, and we've done 2 of those ways. In the last example, we alluded to cross products when we cross multiplied to check to see if the 2 ratios were equivalent, if indeed we had a proportion. So here we're going to use, the concept is cross products. We're going to use cross products to determine whether each pair of ratios forms a proportion. And you can see these are slightly less convenient numbers. You've got decimals in both of these examples, so it's not really easy to say, oh, let me reduce this fraction, let me reduce this other one. Though we can do some things like multiply top and bottom by the same thing. Let's take a look at let's take a look at using cross multiplication or cross products to answer part A. We're checking to see whether 2 over 3.5 is equal to 8 over 14. And therefore, I actually put, this would be a question mark here, like, are they equal? Not that they are equal. I don't know. We'll find out in a moment. So what we're going to do is multiply straight across. I'm going to multiply here and multiply here. And if the answers are the same, I know that I've gotten the correct answer. 14 times 2 is pretty easy for me to do, and I get 28. And then 3.5 times 8 takes a little bit of time, but if you do it, you get 28 as well. And because of that, the 28's on both sides, we know that it is that they are equivalent. We know that both of these ratios form a proportion. We're going to do the same thing on this side. We'll multiply these 2 numbers together, and we'll multiply these 2 numbers together, and we'll see what we get. On one side, I get 0.75, and on the other, I get 0.63, which clearly shows these are not equivalent in neither of these. Neither are these, therefore we do not have a proportion in part B. The beauty of cross products is that it gives us the opportunity to solve proportion problems where we have variables, and so that's really, really helpful. So we're going to cross multiply, and I know we've done this before, but it's always good to kind of see it again. So what we do is we know that these 2 multiplied by these 2, these 2 multiplied together should equal these 2, so we have 10 times 3 equals 5 times x, or 30 is equal to 5x. Since 30 is equal to 5x, I'm going to solve for x by dividing both sides by 5, and finally I get that x is equal to 6. So that is what would satisfy this equation, x equals 6. On this side, we have the same situation, except we're going to be multiplying 7 times x minus 2, and we didn't have a situation like that. When I do that, when I multiply 7 times x minus 2, I need to put the x minus 2 in parentheses. That's equal to 14 times 2, and then I can proceed. So I'm going to distribute the 7 all throughout, and I get 7x minus 14 is equal to 28. With a little bit of ability in solving, you should be able to see that 7x is equal to 42, and therefore, let me draw an arrow up here, x is equal to 6, because obviously I would divide, let's see if I could do that, divide both sides by 7, and then I get that x is equal to 6. Okay, so in example 4, we're talking about a situation where we realize that there's kind of a trend, right? In the past 2 years, a retailer was able to open 232 stores. If that rate of growth remains constant, how many stores will the retailer open in the next 3 years? So over a 2-year period, I know that 232 stores have been opened. So that's the relationship that I'm going to use to answer this question. So after a 2-year period, 232 stores were open. We're trying to figure out what happens after 3 years. And so we need to call this x and work out the details. The first thing I will do is cross multiply, and I get 2x is equal to, I'm going to just multiply 3 times 232 and get 696. And after that, I will finally just solve for x by dividing both sides by 2. And finally, I get that x is equal to 348. In example 5, we have a scale models problem. The scale on a map is 3 inches to 10 actual miles. So the length of the trail is about 1 1/8 inches on the map. What is the actual length of the trail? So when you have a problem like this, we should do 3 inches is to 10 miles as 1 1/8 inches is to x miles. Now that our proportion is set up, it should be pretty simple to deal with this. However, this fraction might be troubling some people. If you'd like, you can write 1 1/8 as an improper fraction so that we are left with, 9/8. That might be a little bit easier to deal with. Let's try that. So I know that the product of these two must equal the product of these two. So I'm going to write it as I know. 3 times x, or 3x, is equal to 10 times 9/8. I can cross cancel to simplify, so I get 5 because 10 goes into 2 5 times, and 2 goes into 10 5 times, and 2 goes into 8 4 times, so that my problem looks like this. 3x is equal to 45/4, and we can solve this. What we need to do is to divide by 3 or to multiply by the reciprocal, which is 1/3. When I do that, the 3's cancel out. I'm left with x is equal to, I'm going to cross cancel here. 3 goes into itself 1 time, 3 goes into 45 15 times, so I'm left with 15/4. If you'd like, I'm very happy with improper fractions, but if you like, you can write that x value. I'm going to draw an arrow over here so we can see what's going on. If you'd like, you can write that x value as 3 3/4, which makes sense. That's fine because x refers to miles, so we can talk about 3 3/4 miles. So we've come to the end of a pretty long video, but definitely take note of the assignment. Make sure you get it done, and I look forward to seeing you guys next time in class.